Ladies and gentlemen, welcome to the ICE Technical Meeting, Climate Change and How Civil Engineers Can Respond. This event is brought to you by the Institution of Civil Engineers. My name is Alfredo Wijaya from ICE Student Chapter Binus University, and it is a pleasure to act as your master ceremony in this event. Before we start, allow me to read the rundown of our event this evening. First, I will be reading the rules of the webinar. Second, there will be opening remarks and introduction by our moderator, Michael Dobie, to start the presentation of our speaker, David Parry and David May, this evening. The event will then continue with a Q&A session. Ladies and gentlemen, for your own convenience, please pay attention to the following rules. For the online audience, you can ask your question to the speaker by pressing the raise hand feature located at the bottom of the screen. The question should be in English. You can raise your question after the presentation of the speaker. You can also raise your question from the Q&A feature located at the bottom of the screen if you prefer the moderator to read your question. For audience who attend events at the Eastern Promise, Kemang, the moderator will later get you throughout the Q&A session. Now, I would like to invite Michael Dobie to give his opening remarks and guide us through the session. To Michael Dobie, the time is yours.
Okay, we're just doing some fine tuning. Right. Thank you very much. I think we still have a few people in the process of joining us. We'll just we'll wait until we start the presentation for a few minutes. Our presenters are here, they're ready to go. They're in fact fueling up at the moment, so they'll definitely be in good shape. Actually, before we start, I'd just like to say one little thing, that one of our last events was our structural challenge, which was held in this room. And actually, the intention was to present the prize and the cup to the winning team, who are mainly in front of me today. And I'm going to have to admit that I haven't got it ready. So I hope that the multi-bang-on team will come back again next time, help us with our next presentation, and I'll make sure we have the cup and the prize ready for them so they can be presented. It was a very good evening, the last structural challenge. We had, I think, 6 teams, and some very good bridges were built, but it was a fine margin, but they certainly thoroughly deserved it. So that was a very good evening. Anyhow, I think now we would like to get this event underway. So we have 2 speakers tonight. And if you've seen the notice, you'll know that they're both called David. We have David Parry and David Mee. If you like, the main presentation will be coming from David Parry, and then David Mee has some specific information. I think you should know that the topic today is really about climate change and climate change related topics. I think what's going to be interesting is learning something about the way like climate change and effects are measured and monitored, the models that are being used. This is what David Parry will talk about. And I think it's a really interesting start, because it gives you an introduction to some of the terminology that you'll hear used when people talk about climate change and the way it is being put into numbers and monitored and so on. Now, we're very lucky to have this presentation tonight. Now, David Parry he'll tell you a little bit about himself in a minute, but he's not an engineer, but he's actually a soil scientist of origin, but he's lived and worked here in Indonesia, and he's worked with engineers for many years. So I think he's very familiar with what engineers get up to. And I'm very much looking forward to hearing his presentation tonight. So he's going to set the scene, if you like, with more perhaps background information on some of the issues and aspects of climate change. So that'll be the first part of our presentation tonight. And then David Mee is one of our committee members. He's the country representative of the ICE for Indonesia. And he's going to provide some interesting information and background about what engineers might consider in terms of materials and other procedures and systems that they use to help contribute, if you like, to the targets of reducing carbon emissions. Because I think, as you probably all know, most countries in the world have now set targets to essentially become what is being referred to as carbon neutral, whatever that might mean, and we might hear a little bit about that as we go along. And the targets are still, they seem to be quite a long way off. We're talking about maybe 2050 or 2060, or some people achieving certain targets before that. But the times will accumulate very quickly, and we'll soon be reaching these dates. And the targets are immense, what people are promising to do. So I think understanding some of the background and the way engineers can contribute to it, I think is really important. And the more we learn about it now, and the more we hear about this kind of information, I think the better. I think maybe one little point I'll add before I stop talking, because we have our speakers who are going to talk to you properly in a minute, is that often I think engineers and people, they think, well, look, I can't make much of a contribution to climate change. It's such a huge thing. I mean, what can I do to help? And the point is that it's a bit like a general election. In a general election, you might say, my vote's not going to do much. It's one vote. But the point is that everybody does need to vote in a general election to get a result. And so I think that the contribution to climate change and reducing the effects of it is a little bit like that, what I call the general election voting issue. Yes, your contribution is small, probably, but if you add them all together, it becomes big. So don't think that your little efforts and ideas would not be a big contribution. They are all going to add together. And I think that's a very important way for you to think about this. So when you start to work on projects and so forth, you can start to think about the issues and seeing how you can help in the way you design something or the way you specify materials or whatever it is. And I think what we're going to hear this evening is going to be a very good introduction to people to help understand where those contributions might be, what they can possibly do. So I think I probably said enough. I mean, two good friends tonight, and it's really a pleasure to have the David team ready for action here. So I think David Parry will speak first, and then David Mee after that. So David, I'd like to hand over. I hope everything will run smoothly. We have the equipment well organized, I think, here. Thank you very much.
Thank you very much. My name is David Parry, and as Mike has said, I'm actually not an engineer. I'm a soil scientist by training, but as he said, I've worked with engineers for nearly 50 years now. Although it doesn't seem to be advancing technical here, great. And in that 50 years, I have come to have enormous respect for civil engineers. And along the way, I've also learned a bit about civil engineering. Is it working? It doesn't seem to be working here. Am I pressing the right button? Okay. Well, we're back on the now talk format. Mike's already said a little bit about this, but I will provide background to the talk, then describe the rationale for using regional world climate rather than an average world climate, the starting point for civil engineering interventions. I'm going to focus on Jakarta's rainfall variability on these topics, and that will take about 20 minutes. And then David will elaborate on the use of more sustainable construction materials and engineering design initiatives for reducing the project's carbon footprint. About 10 minutes. And then as a Q&A session, 15 minutes. And closing remarks by the chairman, Phil Woodmansey. Unfortunately, I think Phil can't be here, so Mike will assume that role. All right, background. Soil scientist, land use planner, remote sensing specialist, not an engineer, sorry guys. But have worked with you for over 50 years on a variety of infrastructure development projects in Africa, Middle East, subcontinent, and Southeast Asia, including 40 years in Indonesia. But with my background in climatology, meteorology, and the physical environment, it seemed more appropriate to focus on climate change and how civil engineers respond, rather than regale you with my sort of possible talks on my other hobbies, like Jakarta's collective rainfall data for 30 years and the history of the mapping of Southeastern Asia. So that may be another time. But tonight it's the environment and climatology. So much of the material referred to in this talk comes from a paper co-authored by David and myself. But we've got Scott Younger, fellow of the Institution of Civil Engineers, who many of you will know. And I believe he was the founding father of the Institute here, or chapter. I may be wrong there. And he was the lead author. That paper was published, I think not last year, I think it was published at the beginning of this year in the Proceedings of the Institution of Civil Engineers. This is the actual reference, if any of you would like to see, if you haven't actually already seen it. Preparing for the Future, the Impact of Climate Change on the Civil Engineering Profession. Lead author, Dr. Professor Scott Younger, co-authors David, two Davids. Scott, unfortunately, is not here. He can't be with us today, either in person or online. But he suffered a severe stroke in 2019 and was medevac back to the UK. He has fully recovered mentally. His faculties are sharp as ever, but physically he's still partially paralyzed with his right side. So he's making progress, and we wish him the very best. And maybe one day he'll get back to Jakarta. Now, some basic climate facts. Actually, Mike mentioned I'm going to discuss climate policy. Well, I'm not actually. That's a topic I could spend a whole lecture on. But I will do some basic stuff, which I think will be useful background for those of you who are not so familiar with this. Now, the IPCC, the International Panel on Climate Change, Intergovernmental Panel on Climate Change, in its most recent report, states that the link between the rise in man-made GHG, greenhouse gas emissions, and the increase in global average air temperature is unequivocal. Now, the main greenhouse gases include water vapor, carbon dioxide, the one we hear most about, methane, nitrous oxide, and ozone. Also, the hydrofluorocarbons, the so-called HCFCs, and the hydrofluoric, the HFCs. These, as you consider, derived to the 70s with the destruction of large ozone hole in the Antarctic. The chlorine in these hydrofluorocarbons actually attacks the ozone and destroys it. This resulted in, I'm sure many of you know, the Montreal Protocol of 1989. Now, this is they phased out these HFCs, so CFCs, which used in refrigerated refrigerants and air conditioners units. And they were very successful. It's the most successful international treatment of this kind of after most with Kyoto Protocol. It's still in place today. The ozone has recovered. And many of these are actually banned, particularly in the United States. We have to find alternatives. Now, at COP15, COP stands for the Conference of Parties. That was 2015 in Paris. Countries pledged to reduce greenhouse gas emissions to zero within 30 years, replacing fossil fuels with renewable energy, preventing planet warming by greater than 1.5 degrees Celsius above pre-industrial levels. Now, to give you an idea, pre-industrial revolution, let's say 1750, the CO2 levels in the atmosphere were around 280 parts per million. Move on to the 1950s and 1960s, it reached 310 parts per million. I mean, parts per million more. 11% increase over 200 years, so nothing really spectacular there. It's up at 0.06% a year. Now, by 2022, today, the level is 4.5 per million CO2. That's a 37% increase over only 70 years. At 0.52% a year. Now that's practically 10 times the previous years. So things are accelerated, hence the concern for accelerated anthropogenic, in other words, man-made global warming. Now, the main cause of increased greenhouse gas emissions, increased use of fossil fuels, coal, and its derivatives, probably the wrong word here, but I mean heat, lignite, and just like the different forms of coal, very, very rock hard anthracite with a very soft heat and brown coal lignite. And then petrol, oil, diesel, and gas. These are used for transportation and electricity generation to power those industries. Deforestation, land degradation, and land use changes. So there's been huge deforestation over the years. A lot of land is degraded, erosion, so on. And land use changes include the once forests have been cleared, certainly in Indonesia, much of the forests is replaced with monoculture, oil palm, and other crops. Increased livestock farming, with beef production more than doubling since 1960, and chicken production actually has risen 10 times. So, with increased livestock farming, of course, you get increasing amounts of methane gas, which is even which is a much more aggressive warmer in the atmosphere than CO2. Something like it's 27 times more. And the increase, you get competition, of course, for land, for growing food, and for grass, livestock. So there's competition all around. So this is another reason why was very much concerned about increased livestock farming. Remember, countries like Australia have over their economy. The other thing, of course, is the world population has grown exponentially, especially since the beginning of the last 200 years or so. And you can see on this graph here the rise in population. With such high population now approaching about 8.5 billion people. That means 8.5 billion consumers, and so much greater threats to all forms of resources. So average world temperature, let's just discuss this for a moment. This is important because average world temperature is a convenient statistic for detecting and tracking changes in the Earth's energy budget. At any one time, cold parts of the Earth are likely to be 100 degrees Fahrenheit, 55 degrees centigrade. That's it. Antarctica, Sahara Desert. But we, as humanity, we do not live in an average world, but we live in specific parts of it with different ranges of air temperature, rainfall, snowfall, and sunshine. Our long-term status of these meteorological parameters in every country and region on the planet form the basis of the science of climatology. Now, the ancient Greeks recognized 3 latitudinal climate zones in the Northern Hemisphere and 3 in the South: frigid, temperate, and torrid. Now, since then, there have been many attempts to classify climate, most of them emanating from the 18th and 19th centuries, and probably 10 are the ones that are most used by climatologists. And of these, the Köppen-Geiger classification of the 20th century is the most commonly used and most appropriate. This is just the ancient Greeks climate classification. Here we are, frigid zone. This is a very sensitive. All over the place. There we go. I think you can see frigid zone, temperate zone, torrid, and then this ocean river around the equator. And then it's repeated in the torrid zone, temperate zone, and the frigid zone. I'm afraid they got north, south, east, and west a bit mixed up in this diagram. So Köppen-Geiger climate classification, it breaks the world down into 5 basic climate types. A, which is tropical, equatorial. B, arid. C, temperate. D, continental. And that last one actually is polar. So not too far removed from the ancient Greeks. There's a little more east in there. We're, of course, in Indonesia. We're part of the tropical equatorial climate with these symbols: rainforest, M for monsoon, W savanna dry winter, S savanna dry summer, and then you have in the area you've got desert climates, steppe climates, and so on. Now, under the Köppen-Geiger system, they recognize 32 regional climates throughout the world. And there are subclimates within each. But again, probably something went wrong in this column. Everything's number 1. It should be 1 to 16, and then 17 down to 32 is the last one. Get it on the screen. This is what it looks like on a map. Again, you can see Indonesia is all in the blue. First AF, AW, and AF categories. The desert climate, red, Africa, I think I'll give up on this public useless. Now, two examples, just to put it into context. No sultan, which under that classification is a step D, WD. It's climbing number 30 in the list. In Kazakhstan, I actually worked in Kazakhstan 3 years ago. Experience the winter. No sultan, which the oil capital was some so was renamed Nur Sultan, is the second coldest capital city on earth. The coldest is in Mongolia. So an average temperature of 3.5 degrees C, with lows of minus 37 degrees C or even below. While I was there, I experienced minus 37 and even more. It's cold, continental Sahara climate, dry, and very cold. So an increase, so say the climate models predicting the worst case scenario anyway. By the end of the century, the average world climate would increase by as much as 6 or 7 centigrade, but most models are saying probably around 3.5. So an increase in an average surface temperature by 3 degrees for a place like Northampton for the second half of the 21st century will bring the average temperature up to 6.5 degrees. It's still pretty damn cold. Sorry, I have to go back now. Snake. Look at this. Yeah. Hey guys, I want to go back. I've gone on to the back. Let's do it clear. That's it. Thank you. Up to 3.5 to 6 degrees. Now that's still pretty cold. But it would make life a little bit easier for the people who live in Northampton. The ground is frozen for 5 to 6 months of the year. So with that increase, 3 degree centigrade increase in temperature, average, the ground would be less frozen for less time, and it would result in some improvements in their agriculture, timing, use of power for cooling and for heating. Now, the other example is Asmara. Now, Asmara is the capital there in Australia. I worked there in 1970 for a short period. Very beautiful city. It's at 2,325 meters. It has a tropical ceramic climate with a dry winter, so it's AW, and a mean annual temperature of 17.1 degrees centigrade. An increase in average surface temperature by 3 degrees centigrade for the second half of the 12th century would bring the average temperature up to 40.5 degrees C, similar to temperatures in humid subtropical climates, CFA, but without the attendant rain. Now, this will cause crop changes, increase in the use of power, residential cooling, and added stress on water supply. So those are just two reasonably extreme examples of what climate change, predicted climate change could do. Right. Now, we're concerned mainly here with Indonesia. So Indonesia's regional climates, as mapped by Köppen, they are equatorial climate, monsoon climate, the blues there, little tropical ceramic climate in some areas, and some up in not Indonesia, but of course in Southeast Asia, Vietnam areas, you've got the rural oceanic means temperate oceanic climate. But we're concerned with Indonesia, And within Indonesia, within, I would say, three subclimates, you have a great variety, huge variety, as many of you have experienced. Now, the climate, one of my hobbies has been collecting daily rainfall data for 20 years, a rain gauge in my garden. And I started in 1992. So I finished, well, I'm still taking them, but for the 30-year record, I finished officially on December 31st, 2021. Now, in the analysis, when you look at the climate stations in and around Jakarta, there's Tanjung Priok, and then there's Soekarno-Hatta, and then South Tangerang, and then Halim, Badana, and then my gauge at Lebak Bulus. And then for a comparison, or just put everything in context, I've got figures for Bogor. So 30-year records, these are the World Meteorological Organization codes for those stations. These are the long position of those stations, but this is their altitude above mean sea level. 3 meters, 11 meters, 22 meters, 28 meters, 47 meters, and the Bogor station 207 meters. Now look at the range of rainfall. 1,815 millimeters averaging at Tanjung Priok over 30 years. Sukarno-Hatta 1658 since the Sukarno-Hatta was opened. And then in South Tangerang, 2,265 over 30 years. Then Halim, 2,374. My rain gauge, 2,799. And then the Bogor one, 3,765. So that's quite a huge range of rainfall data. Rainfall averages. So, what can we say about this? These data were subject to a range of statistical tests, including the calculation of the mean, standard deviation, coefficient variance, student T, Man-Kendall trend analysis. We've already carried out all the data to determine consistency and whether any statistically significant trends can be found over the full period of record, as well as on a decadal basis. 92 to 2001, 202 to 211, 212 to 221. So the analysis reveals the existence of 3 consistent and well-defined annual rainfall zones over the EKI Jakarta that differ significantly from each other by between 500 millimeters and 984 millimeters over a city whose area is actually only 626 square miles. Now that's quite remarkable. I would challenge any city in the world to come up with such rainfall variability within its city limits. The rainfall increases in amount from north to south over a distance of 29 kilometers and an elevation range of 0 to 50 meters. These rainfall zones, I've labeled them A, B, and C, within the city boundary have been identified and mapped. The boundaries of the zones are based on a combination of isohyets and conflicts. It is believed that the increase in land surface undulations and roughness between the 30-meter and 50-meter contours is mainly responsible for the increase in rainfall gradient between zones B and D. Now there is the map. First time it's been shown in color. So there's zone A, Now that's the confluentials there. Then two zone B, or zone B with the 20-meter contour interval running through the middle, going down to the 30-meter, and in fact down towards the 40-meter. So B is the biggest of the zones. And then C, down in the south here, with the higher rainfall. So the current thinking that extreme rainfall events are becoming more frequent and intense is supported by this study. The ICE-Jakarta climate station shows more frequent and intense REs. RE stands the abbreviation for rainfall events, especially in the last decade, compared with the two previous decades. These extreme rainfall events in the decade 2011 to 2021 caused 6 major flood incidents in the city, from 2013 to 14 to 15 to 20 and 2021. Twice the number that occurred between 1992 and 2012. You had severe floods in 96, 97 and 2007. The variability increases for all parameters at all stations during the last decade to 2021. As the finding resonates with trends worldwide with increasing climate extremes and climate variability. Now, for Jakarta, this is where this is the challenge that begins. Well, in 3 distinct rainfall zones, when you are designing for your different types of infrastructure, the flooding, the housing, the roads, which do you use? Do you use all 3? Do you use a specific one for the zone which your project's in? This is something that is a challenge for civil engineers to work on. Now, this is the last few minutes on how we're doing.
Perfect.
Okay. Well, climate drivers of this rainfall variability. Now, this is Indonesia is arguably has the most complex climate or set of regional and local subclimates in the world. The Indonesian agency, the BMKG, Badan Meteorologi, Klimatologi, Geophysica, classified 293 areas of different rainfall characteristics across Indonesia, reflecting its enormous complexity of the heterogeneity. Now, climate variability in Indonesia is affected by global, regional, and local climate dynamics, including, of course, the Asian monsoon, which you will all learn about at school, and is called the terrible floods in Pakistan. The ITC said the intertropical convergence zone. This is the continuous belt of low pressure either side of the equator, where the trade winds of the northern and southern hemispheres come together, the southeast trade, the northeast trade. Those of you that watch the news, the weather forecast, you'll always see this belt either side of the equator with cloud ringing the globe. And of course, we've got the so-called El Nino Southern Oscillation, or ENSO, with its warming El Nino and cool La Nina phases. Now, in addition to that, we have a thing called the Indian Ocean dipole, also known as the Indian Nino. It's an irregular oscillation of sea surface temperatures in the western Indian Ocean. It becomes alternatively warmer, the positive phase, and then colder, the negative phase, at the eastern part of the ocean. The positive phase is associated with drought conditions, and the negative with high rainfall in parts of Australia and Indonesia. Then you have another phenomenon called the Mann-Julian oscillation, the MJO. This is a major fluctuation in tropical weather, which occurs on a weekly to monthly timescale. It's a permanent feature of tropical weather characterized by a pulse of cloud and rainfall near the equator that moves eastward, typically recurring every 30 to 60 days. Again, it has positive and negative bases like the ICE-JLA, like the IOD. That influence rainfall patterns around the Indian Ocean, including Indonesia and Australia. Then local meridional Hadley circulation and the more zonal world circulation change in each phase of the Battle oscillation, causing enhanced or suppressed convection of Indonesia. Finally, you have local scale, diurnal sea, valley breeze circulation, and of course, orographic rain. So you add all this lot together, and you realize just how complex the climate of Indonesia is. And with such complexity of the atmospheric mechanisms, creating the weather patterns over Jakarta, Jakarta and Java Island, separating the major drivers of weather from those with less impact is very difficult. And of course, it's way beyond the scope of even the paper I wrote here, certainly in the scope of our discussion. I just put this down because some of you may know of these things, and I think it would be useful for you as a synopsis of these major drivers. But with Indonesia, the data that I had did reveal that there was clear, good correlation shown for all 5 climate stations between the mean annual rainfall and the occurrence of strong El Nino and La Nina years, with the well below average rainfall in the former and above average rainfall in the latter. This is just a quick shot at the intertropical convergence zone. See the northeast trade ending, coming in, moving westwards, southeast trades coming in south, again bending, moving westwards. Okay, so this is the last slide. Jakarta annual rainfall during strong El Nino and La Nina years. So you can see there is quite a good correlation. 1997, with the La Nina year, El Nino year rather, so 1,200 or 1,267 Tanjung Priok. 1,000, just over 1,000 very reached the Jakarta. South Tangerang 1.6, well 1,600, a bit went to there. We're now 1,700, Bogor 2,800. But again, remember, Bogor Station frequently has well over 4,000 millimeters, so that's a low for a year. That was the big El Nino year. And then 2006, 1,300 Tanjung Priok, 1,252 at Resort, at Jakarta, 1,800 South Tangerang. I have 1,900, nearly 2,000. Bogor just under 3,000. Then we have 2011, just 1,189 Tanjung Priok, 884 at Jakarta, under 1,000 millimeters. And then South Tangerang just over 1,000 millimeters. Then of course I have just over 2,000, and Bogor we have 2.8. And then the mean. So the mean there, these are the means that for the normal years, for 1,800, 1,600, 2,2, 2,799, 3,7. So a really good, strong correlation there. And then we have the strong La Nina years, and again, you can see the result here. Tanjung Priok 2,2, Jakarta at 2,000, South Tangerang 3,000 millimeters. 11 Borders will have just under 3, Bogor 4,700 at Bogor. And then in 2019, they are 22, 25, 29, 37, Vogel over 4,000. And then 220 is the last one. Yeah, no, one before the last. 24, 1925, 4.5, 4,500 in Lebanon, and 4,000 in Vogel. And then the last one, sorry, no, that's it, because these are the averages again, so you can see. So there you are. That's all really I have to say. You found it interesting, and I'll take any questions probably after David. Thank you very much. Right.
Is this all?
It wasn't too much.
You want to?
Yes.
I don't think actually. I don't think I need it. I'd just like to introduce myself. I'm David Mee. I'm the Indonesian Association country representative for the ICE Jakarta Association. Can everyone hear me?
Yes. I don't know if people can hear you on the internet.
Much better like that.
Yeah, for here, but what about online? Can someone confirm that on the internet they can hear me? So, okay. My part of this talk is trying to make the concept of climate change relative to civil engineers. Now, we know, and the media has been full of what ordinary people can do about climate change in use of their car and insulate their house and the type of energy that they purchase. But this is more to do with civil engineers, both in the future and at present, and how they can affect a reduction in carbon dioxide or methane production by what they specify in their work, in their projects. I've started with this frontispiece showing a city, and on the left-hand side shows a pretty miserable, polluted city, and represents what will happen if we do nothing about climate change. And the right-hand side is a bright green future, and hopefully countries will become move towards a carbon net zero and even beyond, because I believe that those that put the carbon up there should be the ones taking it out, which is originally the UK and later the United States, up till just about 15 years ago, when perhaps China took over as the main polluter. Unfortunately, that's not going to happen until 2050 or 2060. I'd hope to show a few daisies here, because the two Davids will be pushing up daisies by the time we get around to 2050. The title is Climate Change, New Civil Engineering Materials, and how can civil engineers be more sustainable? Actually, it's about new civil engineering materials and also a new concept of nature-based engineering, which will be in the second part of the talk. So I'm hoping this is going to disappear. How do you get? Okay, so my presentation will be basically looking at materials, carbon dioxide footprints of common civil engineering materials. specification of new materials with lower carbon footprints and manufacture of concrete and other products from renewable sources. And then third, materials made from carbon capture. Fourth, absorbing carbon dioxide into concrete. 5, nature-based and hybrid engineering solutions. And then river management and flood management using nature-based solutions. And then nature-based solutions in sustainable urban drainage systems. So 6 is really about more rural areas and the sort of irrigation areas we have in Indonesia. And the 7 is about the cities where an awful lot of people are moving to these days, and emphasized by the first picture. So a carbon footprint of manufacturing engineering materials, and starting with steel. Steel on average takes 185 tons of carbon dioxide, or emits 185 tons of carbon dioxide, equal to about 8% of global CO2 emissions. That's to produce 1 ton of steel. So that includes not only mining the ore, but also transporting it to the steel factory. And then once you've got it there, refining it, usually with either coal or electricity made from coal. So it's a huge contribution. And perhaps we should think about, can we either make steel in a better way, or can we find an alternative to steel? And then ordinary Portland cement used in concrete produces 0.62 tons of carbon dioxide in cement per ton, which is also a lot of carbon dioxide. So we need to look at a way of producing cement with less carbon dioxide. So that when we mix together, one average of 1 cubic meter of concrete contains 0.28 tons of CO2, or emits that amount of CO2, about 0.1 ton per ton. So about 10%. Reinforced concrete depends on the weight of the steel. On average, we can assume about 0.39 tons per ton of reinforced concrete. 1 ton of fired bricks contains 0.23 tons of carbon dioxide. 1 ton of stone masonry we can taken from the quarry or the riverbed, and the distance of transport depends on it, but we can assume 0.07 tons per ton. Vegetation absorbs CO2 over the project lifetime, so it does the opposite. It absorbs carbon dioxide, but it has a small carbon dioxide component of transport and fertilization during placement. We normally have to provide some fertilizer when it's a young shoot. So what can we do to reduce our carbon footprint? Support changes in renewable manufacture of concrete and construction steel from renewable sources such as steel. And I understand that this new prototype factory in Sweden is making cement from hydrogen and from liquid salt. I'm not quite sure what liquid salt does, but liquid salt is also can be used in cement manufacture as a heat source instead of coal or gas or whatever you burn to heat up the cement components. And then moving on from steel made with hydrogen, which probably reduces it down to about 50%. Carbon nanotubes, CNTs, and carbon fibre made from carbon capture by electrolysis and from these materials. And there's a Canadian company called Carbon Core making something which calls the Genesis device. And if I click down here, we should come up with the Alberta Carbon Conversion Technology Centre. So they're developing a system of making carbon fibres from captured carbon dioxide. They show how they combine CO2 and air in this electrolysis system with a carbonate in the center. And it produces oxygen and carbon. So it strips the oxygen out of the carbon dioxide and produces these nanotubes as fibers or as rolls of fiber or strands that can be woven together into a dark material that we can use for reinforcement. And thirdly, this is another way of capturing carbon in a greenhouse using what is Indian hemp. It looks very much like, and it's very related to a product that some people like smoking. But actually, Indian hemp has very little of the part that is used by that sort of person. It's used as a material. And it's 20 times more efficient at capturing carbon than trees are. So grown in a very long greenhouse where you feed in the carbon dioxide, say from a coal-fired plant or a steel plant, it can, not so much when it's young, but once it starts to grow, it captures carbon very quickly. And then we can use the fiber from this material for all sorts of construction projects, which I'll show in a second. And then also this material can also be used to make graphene. There's a company in Canada also making graphene from this material. I'm not quite sure what the process is. I put the internet link down at the bottom. So let's have a look at 1 hectare of industrial hemp can absorb 15 tons of CO2 per hectare in 4 months. It takes 20 years to store 6 tons per hectare. So you can see there's a huge difference in 1 year. This can capture 15 tons of CO2, if not twice a year. Now, I just want to show you some of the materials that are made. Carbon and fiber and graphene made from the electrolysis of captured carbon allows steel rebar to be replaced in reinforced concrete with carbon fiber polymer. Carbon fiber reinforced polymer, CFRP, rods. And here you can see the rods used for reinforced concrete instead of steel. So we can in the future we'll be able to build reinforced concrete without reinforcing rods. On the right hand side you can see a beam made of carbon fiber instead of a steel beam. In the center here there's a picture of carbon fiber mesh made for thin panels and floor slabs. And I'll show you something made from these a bit in the next slide. For existing structures that perhaps have started to age and start to crack, we can reinforce them with carbon fiber CFRP panels here. And then on the right-hand side is a picture of what's called hempcrete, industrial hempcrete, which okay. Well, unfortunately, I can't see that. Yeah. Okay. So on the bottom right-hand corner, we've got what's called hempcrete, which is hemp mixed with cement that produces very high insulation blocks. that can be used instead of concrete insulation blocks or the sort of insulation that we normally use. The material on its own can also be used for insulation without the cement. So this is a very spectacular architectural roof made from hempcrete. This version of hempcrete must be impermeable, but it's quite a stunning photograph. This is I think it's some sort of bus shelter made from carbon fibre reinforcement. And that's also, you can see how narrow the member is. You can make it far thinner than reinforced concrete. Perhaps this is just 5 centimeters thick. So it's become a very flexible architectural material. And here's a bridge made from the same carbon fibre reinforced polymers. I'm not quite sure where it is, but you can see it's quite a versatile material that hopefully civil engineers in the future can specify. It may take a little time for these materials to come to Indonesia, but it's worth our engineers here keeping an eye on these materials and seeing when they become available. This shows a 3D printed house made with graphene reinforcing the concrete instead of steel. And apparently you can make a house for about $6,000 or $7,000. You just need to get the land, bring the equipment and the right company, and help design the house, and they just print it straight off like this. And you see the gaps in the walls are for the insulation. And this is quite a spectacular house built from 3D printed graphene concrete. So if we move on, we can then train carbon dioxide into concrete. It doesn't stay as carbon dioxide. It becomes you inject very small bubbles of it, and it nano-sized, and it produces calcium carbonate, which becomes embedded in the concrete. This makes the concrete stronger, enabling mix optimization while eliminating the CO2. It's used on very effectively on slag concrete. Slag from iron ore works produces concrete with high salt resistance from maritime works. It's also a very hard concrete and very good for erosion resistance. And here we have a picture of a cylinder of captured carbon dioxide held in a tank, ready to be injected into the concrete as it's made and then taken away. Now I want to talk about nature-based and hybrid engineering solutions, because this is something that Indonesian engineers, particularly those working in drainage and flood protection and irrigation, can use a lot of. So first of all, talking about landslide stabilization, if you look around the hilly areas of Indonesia, you see a lot of landslides. It's a very big risk, and so stabilizing them and making them productive in terms of capturing water and holding back water from flooding is important. Also, embankment stabilization, riverbank and drain bed protection, check dams, and infiltration capture, particularly in cities, is very important, because cities in Indonesia have a terrible problem dealing with intense rainfall, particularly if there's a river running through them that has high flood levels. So this is a landslide I came face to face with about 3 weeks ago in Palu that was caused by the earthquake. And you can see the satellite images before the earthquake when this was a green forest, and then after when it was, in fact, some of it had already been cleared. But after the earthquake, this occurred, and it's washed a lot of sediment into an intake for the water supply for Palu. So what can we do about it? Well, this was my design, and this is the cross section of the landslide, and I'm proposing to stabilize most of it with what is called vetiver grass, which has very deep, strong roots. They go down and hold the soil. Also, I've shown on some of the very small horizontal sections, I've shown bamboo, because bamboo has roots that move underground, called rhizomatous, that also help to hold the soil. And then where you've got a bit larger of a step, I've shown lantoro. Lantoro gung is a crop that produces leaves that it's a kind of pulse, and the leaves fall from the tree and they help to nitrate the soil for the grass to grow. It's a legume. So this is my solution, and the top of the landslide happened. You retain the natural species. Now this, I don't know, might be. This was what I proposed for a liquefaction landslip in Palu, where they proposed a geogrid, and so I said, well, perhaps to grass the surface, we could also use vetiver to make a three-dimensional grid to hold the soil. Unfortunately, the local consultants changed it to filter material, which doesn't have holes where the roots can go through. So I had to slightly modify it and use less vetiver grass and put in just ordinary grass, stoloniferous and rhizomatous grass. Stoloniferous grass is where the plant projects on the surface and then pops up the next plant, and rhizomatous is where it goes through the soil and then pops up the next bit of grass. So this was a combined solution between a manufactured geotextile and a nature-based solution. And I think where you have severe situations, it's good to combine the two. In fact, vetiver grass, you can design it. They've done tests on its tensile stress, so you can combine it in a physical calculated design. Now this is a river or stream that's been redesigned in Europe, and you can see on the right-hand side, it's got room to spread in a flood. It's reintroduced meanders into the corridor, which give it more storage. It's more of a natural shape. It's providing secondary currents to keep sediment moving. And it has an amenity value because you can see the jogging tracks and the walking tracks and places where people can sit out in the sunshine. And the city is moved to the side. On the left-hand side is a recent design to straighten out the rivers in Bandung, and it's in my view is a poor example. And the whole purpose of it is to reduce the river channel so that people can build buildings on either side of it. it's a land developer's dream. But when the severe flood comes, it's going to cause problems, particularly in areas downstream, where because the straight channel has less storage, but it also accelerates the flood to lower areas. And when all the streams are like this, the lowest areas where the poorest people live are the areas that get the most flooding. And they're the people with the least ability to do something about it. So this is above is what I come across all the time in flood control for rivers, is to line the rivers with masonry or concrete. It's a hard surface. It accelerates the flow down to lower areas. It easily cracks if the bank settles. There's no bioremedial action. And it accelerates flows. National design consultants in Indonesia are frequently designing like this. Now, on the not only national consultants. This is a national consultant from Japan that's designed this completely lined channel here and straightened it from the original sinusoidal channel. Down below is part of the Citarum River, where there's been an experiment to plant vetiver grass, and you can see on the left-hand side the vetiver grass once it's been planted, and then in the center after 2 months, and then on the right-hand side after 3 months, you can see it's covering the whole slope. And this grass also has a bioremedial action, so we know how dirty the Citarum River is, but this grass is helping to clean it up, hopefully. Although you can see the river is still a bit of a dark black color. And these deep roots stabilize the soil banks. And actually, when it gets very high, they can be cut down and used as fodder for the local farmers, for the local husbandry. So it has other uses. And this is an example of a riverbank where we've used combined materials. Well, actually, gabions have wire baskets filled with rocks, and they too have a bioremedial action. You know, the water enters quite deeply, and the algae or whatever biological action on the surface helps to clear the water instead of concrete. We put riprap at the bottom in case of erosion, and higher up where there's lower velocities, whereas the effect of secondary currents is not so great around a bend. We have vetiver grass and the other grass in between, which also has a benefit for the local farmers. So this is the kind of design we can put into flood management on rivers in Indonesia and elsewhere. And then here on the left, controlling rivers that are eroding is quite a big problem, particularly in Palu. And on the left is our Japanese consultant's solution for river control, which kind of horrified me, but it's a Sabo dam, which is okay for controlling lahar flows from a volcano, but to me it's the wrong solution for river restoration. And above right, you can see a river restored with check dams made of pitch stone, and below is an example of how I would design a pitch stone check dam, particularly in a boulder river with high velocities. So you would use tetrapods here and then natural or quarried stone here. But in the photograph above, you can see how well the grass has been established, and the velocities that now come through the river are sustainable by the grass surface. The grass is not going to get eroded away because the drops are taken by the drop structures. So this is another, in a sense, a nature-based solution rather than a huge, great concrete dam. And here I'm showing sustainable urban drainage systems that are known as SUDs, and these are very common in Europe. So it's a very common practice to try to get rainfall to absorb into the groundwater very quickly to ease the floods in the river. It's something that needs to be introduced into Indonesia because so many of the cities here are very susceptible to flooding. And as I said, when you get very heavy rainfall in the city, and there's a river running through the city, which is very common in places like Bandung, Medan, so many cities, something like 13 rivers running through Jakarta. You need to try and absorb it. So in close to roads, if we have a grass strip, you can help it by putting in a containing shape, a convex shape to trap the water. So that's one example, and you get a bio-retention area, that shallow depressed landscaped areas, which typically under drain. We rely on engineering soil and enhancing vegetation and filtration to remove pollution and reduce runoff. And here, this in the centre here is an example of a factory or an office where roof runoff can be directed into a pond, and because of danger of malaria and other diseases, you can try and keep larva-eating fish in there and grow water weed to try and help clean the water. And then the idea is to pass it into an infiltration well that spreads the water into the groundwater. And then thirdly, on the bottom is a cross section through what could be a car parking area, but with grass cell blocks. So you have blocks with gaps in them that you fill with soil and grow grass in, and the cars can park over it even in the wet season safely. But the water drains through to a sand layer and a gravel layer to infiltrate into the groundwater. So I think I've just about finished. So, terima kasih. So I hope all our students here have taken notes, and I hope we will send the presentations to them, and hope that they'll keep an eye on the future when they start work and seeing how they can specify new materials or nature-based solutions for their projects. Okay, I'm going to hand over to you.
Yeah, okay. Yes, thanks very much, David. That was a really interesting talk with a lot of very nice ideas, including the occasional geogrid, which of course is nice. Actually, combining with vetiver grass is something I felt was a really good idea, especially if you wanted road embankments to survive overtopping from tsunami. I thought the combination would be good for that as well. So yeah, another one. Okay, so there's one message come online, which I think is really for David Parry, that is. Can you read that?
Yeah.
If you want to get close, otherwise I'll read it. I'll read it for you.
Temperature 1 point already evidence today. Should we be focused on mitigation?
So I'll read it for the people.
Yeah.
Okay, so this is from John Campton. So thank you for your fascinating presentations. Given the catastrophic effects of climate crisis, global temperature rise of 1.2 degrees centigrade already evidenced to date, shouldn't we be focusing all on mitigation, limiting projected rise to 1.5 degrees centigrade with a reference? Wouldn't this mean, this is a big question, wouldn't this mean redefining net zero 2050 to net zero 2030, which is not that far away. You're gonna in front of the
Well, John, yes, that's, I would agree entirely. We would really need to redefine net zero to 2030, but in reality, is that going to happen? And, I don't think it will. So we should be focusing our efforts on mitigation, and there's a huge amount that can be done. And as we talked, David has indicated, there's a lot that engineers can do to help us. But achieving net zero by 2030 would mean some serious reduction in greenhouse gas emissions by India and China. And as we know, they're not willing to do that yet. Last COP in Glasgow, they were the stumbling block to the agreement to limit or reduce, put a limit on GHG, particularly from fossil fuels, because their economies are driven by fossil fuels. So it's not looking hopeful. I think we have to be realistic. And as you say, we focus on much of mitigation as we can in other areas, and while recognizing it's highly unlikely that particularly China and India, or in other words, Russia, or even the United States, will stop their fossil fuel emissions by the climate rise at 1.5.
Can I just say something? Actually, John is a guest I invited, and I see he's already gone back to work. So I'll send him an email with our answer on it. I'd just like to say that I agree. It's a terrible risk. At the moment, we have carbon dioxide at 420 parts per million. By 2060, when China and India have agreed to go be at net zero, not even to take out, to remove what they put up there, we're going to be perhaps at 800 parts per million, and we're going to be facing a 3 or 4 degrees centigrade increase, which is extremely worrying. I think some countries are working to specific improvements by 2030. I know the UK is trying to demand that all cars are electric cars by 2030. The UK is also promising by next year to have closed all its coal-fired power stations, whereas somewhere like the United States already has something like 240 coal-fired power stations still in operation, and they're the country that has put most of the carbon dioxide up there. So I get a bit frustrated when I read Americans commenting that it's China and India that's the big problems, when they're the ones that are really the ones that should be removing most of it now. I think it's up to the UK to, and I think the UK is showing to some extent that it is at least reducing its carbon footprint, and hopefully once we've done that, we'll start removing carbon dioxide seriously to the extent of which we put it up there. Okay, what's the next question?
Well, I think probably I'm going to suggest, because we're well over time now, is there any one question from someone in the room that would like to ask? Any questions from anybody in the audience? I don't think so. Just perhaps one brief kind of combination comment and question. It seems that from your 2 examples, actually some places will benefit from global warming, but I'm really going to assume that the proportion of the Earth that's the case is quite small. There's a lot of effects to the Earth, so it must be horrific. So I think relying on the occasional place that might benefit is not a particularly good idea.
No, that's a good point, Mike. Yes, there will be part, yes, there will benefit if we saw those frozen areas now, very cold areas, they will benefit. So their agriculture will improve, the planting season will come earlier. And there is, of course, fertilization effect of CO2, which isn't. But as Mike said, we shouldn't be relying on positives. There will be positives all over the world, but negative will most certainly outweigh the positive by now. So that's we've got to look for other solutions.
Okay, thank you. Just one last note, I think that I would like to bring the evening to an end. I thank you both David Parry and David Lee, for assembling a huge amount of incredible information. I think a round of applause is certainly well deserved, and I found that excellent. I look forward to getting your material that we can then circulate to everybody who's been listening in today. Yeah, really, I mean, you've had two different ends of the spectrum there, from the overall picture to some detailed ideas as well. And I think that's been extremely valuable. So I'll bring the formal part of this to an end. I think our MC might then draw the whole thing to an end. And once he's done that, then invite everybody to get some curry in a minute, and that'll be the time for you to talk informally to our speakers as well. So thank you, everybody. MC, wherever you are, if you'd like to bring this to an end, then thanks very much.
Thank you, David Parry and David Mee, for your excellent presentation. And thank you also to Michael Dobby for guiding us this session. Ladies and gentlemen, we have now reached the end of the event. Once again, thank you for your participation. We hope we can see you at the next time, at the next event. Finally, good evening and stay healthy, everyone.